So, in order to prove this, we actually need to construct many solutions, which is useful to get for us to understand this problem. So the clue is I take this as a principal part of our solutions. Okay, so here we're trying to construct something like this. ECX times 1 plus omega XC. So omega is considered as a remainder. It's a remainder. Okay. It's because this is equation is a perturbation of this. So solution is no longer that. You add a remainder. But this remainder is not a natural remainder because you have a parenthesis, you have 1 here. Okay. So it turns out that this solution is useful. Now, of course, it's again there's a question how people discover this solution. What is the story? I mean, if you understand this, then people may try this first. Of course, you can try that, right? But however, this one turns out to be is useless because you cannot control that. I mean, you can control the growth of that solution in certain law. But then people realize that if I set the remainder like that, then there won't be a control of that. So here is the omega xc. Okay, so here, because I'm concentrating on the domain omega, so at least in the dimension 3 or higher, I don't have to worry about what happens outside of the domain. So let's just signal this L2 omega. Okay, it's controlled by constant C. It's a constant C which is independent of C. Okay, it may depend on the potential, of course. They divide by C. Like this. That's the length of that. But of course, what it also depends on, like the n, the dimension. It also depends on omega. But key is this one is this C is independent of C. So this means that when C large enough, then this term, the remainder looks small. Now people realize that this equation can be this solution can be constructed in this way as long as this complex vector is large enough. It's large enough. Okay. Now here the construction is different. Okay. So when n greater than 3, so you have to use the Fourier transform plus some kind of micro-local analysis. Micro-local bit, but the basic truth is Fourier transform. Okay. But it's not a regular Fourier transform, so that's why you need a micro-local treatment to get the solution. But so this the construction of this is we're unable to study in this class. It requires some additional work. Okay. So when n to 2, there's an easy construction, another way to construct. So I'm going to say a little bit about n to 2. Okay. So first, we're going to see that how we can use this solution, why this solution is useful in order to produce this, to produce that is complete. So I'm going to show this when n greater than 3. Okay. Now so I'm skipping, so here in the n dimension, when n is greater than or equal to 3, I'm skipping the difficult part and jump to the final stage to show the uniqueness. Okay? So the idea is we're going to think about what kind of C here is in a construct in dimension n to 3. So I'm going to show you depends when n equals 7, okay? When n equals or higher, then follow the same instructions. Okay? Well, what will we take C equals to 1/2 eta plus I k plus L. Now, what is these eta k L? So, eta k and L is in R straight. So these are vectors in R straight, and they're perpendicular to each other. So I'm drawing a picture like this. So here is K, and this L, an angle, and here is eta. Again, it's a right angle. And with the condition that eta is equals K plus L. I think this is true. I don't remember the exact. Yes, square, sorry. Okay? Because, so why is suppose I have three real vectors, okay, with this condition, they are form this complex vector. Now why this complex vector set by this condition? So this implies C dot C. Why set by this condition? Now 1/2 is not important, okay, but in the proof, we're going to take 1/2. That's it for the convenience. So without 1/2, you can, okay. Think about this dot product, okay? So suppose I drop the 1/2, okay? So this is eta, so I k plus L dot eta plus I k plus L, right? Okay? So then you can see you have to use distribution rule. So you take the eta dot this, right? Then eta dot k and L. But you see eta is perpendicular to k and L. So the second dot is eta to k and L will become 0. So the first thing is just the eta square. Okay? Then you take the second part. Now if you take this dot, the eta, again is equal 0. And you take this dot this. So that's create a minus sign, I squared. Then k, so what is k plus L dot k plus L? So this is the 1. Because they are perpendicular, so it's just a k squared plus L squared. Right. Okay, so therefore this is just equal to minus k squared minus L squared. Okay, now because it's set by these conditions, so this implies this equals 0. Okay, so you can see that I can choose the complex vector in such a form. As long as this condition is satisfied, then this is okay. Okay. Okay, so now I have I start from the identity here. Q1 minus Q2, B1, B2, BN, C2, right? Okay, so I'm going to choose B1. B1 is any solution corresponds to the first Schrodinger equation. So I choose B1 to be one of such a solution. So this is C, E, C1, X, 1 plus omega 1 X, C. 1. Okay? And C1 is choosing to be such a vector is 1/2 and eta plus I k plus L. Okay. I choose B1 to be this. Because I'm allowed to choose any solution I want. I choose one like this. And I choose V2. V2 is corresponds to the second Schrodinger equation with the potential Q2, right? Okay. So this one I'm going to choose C2. X 1 plus omega 2, X C2. Okay. And then C2, so I choose a different C. So that's the trick. So we know that these three vectors has to satisfy this relationship, right? But I will be able to change the sign. Okay, so what I'm trying to do is, and still have one half here, the minus eta, for the minus doesn't matter, right? The plus, the ik, and minus L. So with this minus sign, that this corresponding relation still hold. And so therefore, this C2 will still be allowed to, in the construction of the facilities, right? Okay, so once I have that, you plug it in, what do you have? Okay? So you're going to have this times that, right? This times that. So this times that, first, you have exponential multiplied together. Then you can combine these exponential exponent together. You have C1 plus C2. Now what is C1 plus C2? You take C1 plus C2. Then something cancels. N cancels. L cancels. What do you have? Only K left, right? So it's just but one half also disappear because the same term IK one half together is just IK. Now this is the important thing because this, suppose this is just dx, then what is this? Suppose there's no remaining term, it's just the exponential ikx sitting here with this. You multiply these together and do the integration, what do you get? Fourier transform. This term is exactly the Fourier transform of Q minus Q2. Right? Now, so therefore, if you can prove that the Fourier transform of Q minus Q2 equals 0, then this will imply that Q is right? Okay. So then you can see, however, when you multiply V2 through V2, you have remainder here. So here is not exactly this term, there's other term. But for the other thing on the other side, okay? If I put other thing on the other side, so what do you have? The minus omega, then you have again Q1 minus Q2. Then again you have exponential of Kx, right? Okay, then what do you have? Then you have remainder omega 1, omega 2. You have omega 1. I skip the detail. Okay? The plus omega 2 plus omega 1, omega 2. Yes. Yeah, I cannot skip the detail because detail is important. So omega 1, xc1, then plus omega 2, xc2, plus omega 1, xc1, times omega 2, xc2. Then together, ex. You get that. Okay, on the left side, you know this is the Fourier transform Q1 minus Q2 transform at K. Okay. Now, why this is useful? Then we realize omega 1, omega 2 are remainder, and these remainder actually satisfy this kind of estimate. It when goes to 0 when C goes to 0, right? So therefore, you can see that like in here when we define C1, C2, you have eta and L, right? So you can see that there's a lot of things are free there. You can they are not uniquely determined by the initial setting. So what it means is that when you have this relationship, you can see that in order to set value to this relation, you can let K goes to infinity. But when K goes to infinity, I take this free, I fix K, okay? I fix a real vector K that the L goes to infinity. And then of course this will imply that the eta will always go to infinity, right?
But I insist the k to be fixed. Okay, so this is what I'm trying to do. So here in this construction, I fix the k. And let both L and L goes to infinity. But actually, I let it 1 goes to infinity, that's L. And this will automatically imply that the F should also go to infinity, right? But however, these two things are cancelled. You see? These are cancelled. So therefore, what happens is here on the left side, there's no where L and L goes to infinity does not affect the left side. The left side still only depends on K. That's the Fourier transform of this difference. But on the right side, when this guy goes to infinity, the C1, C2 will go to infinity. The length will go to infinity. So this will imply that this will go to 0, this will go to 0, and this product will also go to 0. Well, of course, here there's some additional work you have to do. They are not go to 0 point-wise thing. They go to 0 in the function space. In the L2 function space. Okay? Right? In the function space. So therefore, but however, it's easy to establish some identity. Using identity here, because this is bounded. Q1 minus Q2 is bounded. And this is also bounded, right? It's a bounded function. The length is bounded. But these two are goes to 0 in L2. So use the basic integration estimate. You can see that the right-hand side will go to 0. When L goes to infinity, the L is here. And of course that eta should also go to infinity. But eta depends on L. So for each fixed k, you can see that this process will show that this thing is exactly 0 for each k. Okay. So this shows that the Fourier transform is equal to 0, so the Q will be 2. You get it. So that's fine.
Will we know what omega 1 and omega 2 be? Like what kind of a function it is?
They are the complex function satisfied with S2.
Okay.
So this is a follow from the construction. But however, I didn't say anything about the construction yet. It's follow from the additional work involving the microlocal analysis. They are first constructed by Sylvester in the initial paper. Yeah. So from here you can see a basic idea in the front very common because everything reduced to construct space. This is not a exponentially growing solution. The reason is because this is not the eta here, C here is a complex factor. Okay, so if you take the length of this solution, the length will grow exponentially. It's called exponential growth. And in this proof, the trick is we cancel this exponential part by choosing these factors in this way. So that part is canceled. Everything reduces just a Fourier transform. So for n greater than equal than 3, then that's the basic proof. Okay, first discovered by people. Then this proof has been extended to cover some other equation like Schrödinger equation with backtrack potential or Maxwell equation or electricity, elastic system or those or more complicated equation. Basically, they're all using the same approach. But the construction will be more complicated, of course, especially in the Maxwell case. So, but however, this proof does not apply to A to the 2. Okay, why it does not apply to A to the 2? Because there's a very simple reason. You can see that in the three-dimensional case, you can construct C this way, right? When n greater equal than 3, there's enough freedom for you to do this way. But for n equal to 2, okay, suppose you want C dot C equal 0, there's not much choice for that. Okay, so the only choice is like this. You take K. You take 1K. Okay? Then you take the perpendicular components. The K perpendicular. Or you take the other. There's only two choices. Then you can get C is equal to K perpendicular plus pi K. That's it. I mean, if you try to begin to solve this equation, you will end up with something like this. That means there's only vector available in R2 was satisfy these conditions. Okay. So now you can see that the whole vector, the whole vector here depends on completely on K. There's no other parameter you can choose. Okay, suppose you do the same thing in the 2D case in this approach. Okay, well, you will have this, you will have that. I mean, suppose you choose like C1 is equal to K perpendicular won't have K perpendicular plus IK. And the other one you can choose in order to match here, the second one won't have the minus K perpendicular plus IK. That's the one here, the second one here, right? Now, so that's the only choice. So if I choose this, I still have this. You are still end up with the Laplace, the Fourier transform. That's fine. But the key is that here, C1, C2, C, they are only depends on K. Only depends on K. So how do you make it to be goes to 0? You have to choose large K. The K itself goes to 0. Then you are not fixing the K anymore. K is not fixed. Right? So what you really proving in the 2D case is that you are not showing the Laplace, you are not showing the Fourier transform of that equals 0. You are showing that the limit of the Fourier transform as K goes to infinity goes to 0, equals 0. That's it. You don't get any uniqueness with that. See? So that's the trouble with the n equal to 2. Okay. So therefore, for n equal to 2, we need a different program. But it turns out that n equal to 2 is much more difficult than n equal to 3. Now, the way to think about to handle the n equal to 2 is that in some sense, you cannot move it, you cannot separate these together because it's no good. Because so once you separate, then that's the Fourier transform Q plus Q2. And the other side, what can you say? You can't say anything. You cannot say anything. So what you do is that you will still combine this together like this. So in A equal to 2, okay. So what you do is you can go like this instead of C what wholly depends on K. So you may want to write something like this. That was omega 2 x K and plus omega 1 x K times omega 2 x K dx. Okay, so this is exactly the 0 for any. Okay. So you understand the behavior of the whole thing here is with this remainder. Okay, to find another problem to solve the problems. Okay. So what we're trying to do here in A equal to 2 case, again, I'm unable to give you the whole proof. Okay, but however, I will do my best to describe the idea, a different idea of getting this. Okay. Now, first is you have to understand more about the solution when A equal to 2. Okay. So we take the C with that. Okay. So we're trying to understand what will be the equation satisfied by omega in A equal to 2. Now, if you plug in this into this equation, what do you have? You have this, right? So temporarily, I just write omega. No other details, okay? Minus Q dCx plus omega. Well, this computation actually works for any dimension, but eventually, at some stage, I'm going to use the dimension 2 as a condition, okay? So if you take the Laplace on that, okay, well, using the product rule, the Laplace on the exponential function will become 0 because the exponential function is a harmonic function, right? Okay, then you have gradient of this dot gradient of that, twice of that. So here, on the first part, it's going to
2c, okay? Then you have a dot gradient omega, then times the exponential cs, right? And then plus the ECX to the Laplace omega. So that's the first part. Then the second part is just this. I mean, it's Q ECX. Okay? Then you can see I can cancel all the exponential terms. Exponential part. So you are going to get an equation for omega. That again is the second order elliptic equations. So here, I'm going to show you several results. The first we have to settle is how do we construct solution in A2. Now in A3, I know that this is all from macro-local analysis. We are unable to discuss here, talk about here. But in the A2 case, this equation has an additional reduction, can be reduced to the dy equations. So this is something we can handle. Okay, use a lemma, then show you the construction here. So the first thing is we're going to first, so this one here, some notation I can show. Okay, here, so what is the definition of that? What is the definition of this?